Today, we want to take a graphing approach to talking about partial derivatives. So we're going to start with this contour diagram, which is just a bunch of parabolas. So remember, the contour diagram represents curves where z is constant. So this all represents curves where z is constant. That's what's going on in a contour diagram. So these are f of xy is equal to some constant. And I'll use the mortal constant as I normally do. So if we want to evaluate this function at these points P, Q, and R, we just have to look at what contour each point is on. So here's the point P. It's on, if we just trace this contour where we see the value, it looks like f of P is equal to 9, because that's the contour on which P is sitting. So just so that we see what's going on, f evaluated at the point P is equal to 9. We look at the point Q. Q is on the 11 contour, so f of 11 of f of Q is equal to 11. And R is also on the 11 contour, so f of R is also equal to 11. So what we want to think about is the partial derivatives, the partial derivative of z with respect to x and the partial derivative of z with respect to y at each of these 3 points. Now we're going to have a hard time, since I didn't put this on a grid, we won't be able to calculate these values, but we will be able to determine if z is increasing or decreasing in the x direction or the y direction. So we'll be able to determine the sign of the partial derivatives. So let's determine the sign of each partial derivative at each point. Remember that the sign of the derivative will tell us the direction of the function. The sign of the derivative tells us the direction of the function. The sign of the derivative tells us the direction of the function. So the sign of the derivative, positive or negative, tells us the direction of the function, increasing or decreasing. And we're just going to try to determine whether z is increasing or decreasing in the x and the y direction. So let's start with from the point P. From the point P, if we move in the positive x direction, that is to the right, the next contour that we hit is the contour 7. So in the x direction, it looks like the partial derivative of z with respect to x at the point P is negative. So we'd say that the partial derivative with respect to x at the point P is negative. Because if we move to the right, we're headed towards a lower value for the function. So moving to the right, from P, the values of Z are getting smaller. Because the next contour to the left, sorry, the next contour to the right is 7. So here we are at P on the 9 contour. If we move to the right in the positive X direction, we end up at the 7 contour. So it looks like Z is decreasing in the X direction. So the partial derivative with respect to X at the point P is negative. We could also write this with Leibniz notation by saying the partial derivative of Z with respect to X evaluated at the point P is negative. So we would say that Z is decreasing in the X direction at the point P. Since we have a function of 2 variables, we have 2 partial derivatives. So we also have to look at how things are changing in the Y direction. So if we move to the move up from point P, it looks like the values of Z are going to be increasing. Because if we start at point P on the 9 contour and move vertically, the contour we're headed for is the 11 contour. So we would say that Fy evaluated at P looks to be positive because Z is increasing if we start at point P and move in the Y direction. Or we could also write this as the partial derivative of Z with respect to Y evaluated at P is positive. So if we move up from point P, the values of Z are increasing. The direction of the function tells us the sign of the derivative. And from point P, if we move up, we start at the 9 contour and we head towards the 11 contour. Start at the 9 and we're moving towards the 11. Now, notice that our contours are every 2 units. Given this information, it would be really unfair for me to say, but between the 7 and the 9, there's a -2 contour. That would just be cheating on my part. So if you find that that is the case, either I'm cheating and you should just say, well, Leach apparently wanted to steal these points from me, so what am I going to do? Or I made a typo, which is going to be super common. But one of the things you need to learn when you're a college student is to question everything, especially if it comes from an authority figure. So if you're like, oh, no, I really think this should be if I labeled the answer as fx at p is positive, and you're like, oh, dude, unless you're hiding some information there, I think it should be negative. You need to let me know. All right. So we can do the same thing for the points Q and R, although I realize that I did not give you a piece of information. Presumably, based on the information that I've given you, it would be unreasonable for me to expect you to come up with anything other than 13 for that next contour. If that one drops down to 9 again, and I don't tell you that, I'm just straight up cheating. So if that one is at a 13, if we look at the partial derivatives at point Q, Q is starting off at the 11 contour, and if we move to the right in the positive x direction, then the values of z are increasing. So it looks like fx evaluated at Q should be positive. So fx evaluated at Q should be positive. Or we could write this as the partial derivative of z with respect to x evaluated at point Q is positive. Z is increasing. We start at the 11 contour. The positive x direction means we're headed to the 13 contour. So the reason I'm choosing the positive x direction is that I just have to then look at what's happening to y. If we move in the negative x direction, sorry, not happening to y, what's happening to z. So z goes from 11 to 13 when x increases by positive 1. 13 divided by 1 is going to be a positive ratio. If you move negative x, then it looks like the values of z decrease, but then it'll just be a negative divided by a negative, and that would still be a positive. Just like with slope, if we have a slope that has an increase of 5, a rise of 5 and a run of 4, that makes a positive slope. But we can read that as a rise of -5, but then we'd also have a run of -4. The point is that the signs are the same. So all we're doing is a new version of slope. And if we have a positive rise, and a positive 4 run, that is the same as a -5 rise paired with a -4 run. Five over 4 is the same as -5 over -4. So we have 5 over 4. That's the same as -5 over -4. That explanation was excessively color-coded. So I move in the positive x direction. I just have to look at what's happening to z. If z is increasing, then the slope will be positive because it's positive over positive. A great question. What if z increases when you move both left and right on x? So at that point, it will look like if from a point we're going up in both directions, we must be sitting at the bottom of a valley. So imagine yourself sitting at the bottom of a valley. If you move to the left, you have to go uphill. If you move to the right, you have to go uphill. So think about what your derivative would be if you're at the bottom of a valley. It's coming up in a minute. So it looks like the derivative with respect to x at q is positive, and the derivative with respect to y at q, we're at the 11, and if we go in the y direction, we're headed towards the 13. So it looks like the partial derivative with respect to y at the point q is also positive. So fy at q is also positive. Any questions? All right, let's take a look at the point R. I tried to draw R at the vertex of the parabola, that's the 11 contour. So if I draw this and it looks like R should be at the vertex, it would be cheating for me to say, oh no, it's actually a little bit to the right of the vertex. And at that point, I'm just cheating. Or I didn't really know where R was. So it looks like, let's just make a note of that it looks like R is at the vertex of the 11 contour. So we want to look at what's happening to z as we move in the x direction. So if we move in the x direction, I think I just read your previous question as the opposite of what I was thinking of. But now I can't remember what I said because that was a whole like 2 minutes ago. Oh, wait. So let's look at what's happening at R. So at R, if we move in the x direction, if x increases, we're going from the 11 to the 13 contour. So it looks like f at xr is positive. Oops. And the same thing happens at R that happens at Q. Fy at R, we're going from the 11 to the 13 contour. So it looks like we're going to be increasing in that direction as well. But there's a weird thing that's going on here. I keep trying to use my trackpad to scroll up and down, but this is like a physical piece of paper. Well, that's not actually paper, but you know what I mean. And so I can't scroll up and down with the trackpad. I've gotten too far away from my diagram and I can't just zoom out on the camera. So the other thing that we notice is that if we move to the left from the point R, if we move to the left from the point R, we're also headed towards 13. So if X decreases by 1, Z is also increasing. So if we head to the right, it looks like the values of Z are increasing, but it looks like if we head to the left, the values of Z are also increasing. So in both directions, it looks like we're going from 11 to 13. So it looks like we're going from 11 to 13 in both directions. But the rate of change cannot be both positive and negative. So can this value be both? We can't have a value that's both positive and negative. We can't have a value that is both positive and negative. So what's going on? You might be wondering how I'm going to fit my answer in this tiny little corner of the paper. It's not actually paper, but you know what I mean. How am I going to fit my explanation for what's going on? We can't have a value that's both positive and negative. What's going on? How am I going to answer that question in this small amount of space? And the answer is, I'm not. That's one of the questions that I'm not going to be answering today, at least in class. So it looks like the values of Z are increasing to the right, but it looks like they're also increasing to the left, because in both directions, left and right, we're going from 11 to 13. We can't say that the slope is both positive and negative at the same time. That doesn't make any sense. So think about what must be going on. That'll be our cliffhanger for the day. Any questions? I'm glad you recognize that I'm not going to be answering this question, so you didn't just try to ask that one again. I am not writing on paper. It's like a plastic. It's a reusable notebook. So I can just I have a specific kind of pen that I have to write with. Pilot friction pen. That's not one. And this is an erasable notebook. So as soon as we switched to this format, I wanted to use a document camera, and I was just writing on paper, but I was going through reams of paper every semester. So I needed a ton of notebooks, and I didn't really need the notes afterwards because I scanned them and then posted them online. So I don't need the hard copies anymore. So I just ended up recycling a bunch of stuff. So now I have a reusable notebook. All right. That's why we have the QR code at the bottom. So what this problem was about is thinking in terms of graphs, what we're talking about with partial derivatives. We remember that when we're talking about first derivatives with with graphs, we're talking about the slope of the tangent line, and that the sign of the slope of the tangent line will tell us the direction of the function. Positive slope means increasing, negative slope means decreasing. We are just modifying that for partial derivatives by saying increasing in the x direction and then also increasing or decreasing in the y direction. So we're just breaking what we had before. Sign of derivative tells us direction of function, and including in the x direction, in the y direction. So we want to continue adapting our knowledge about derivatives. We want to continue adapting our knowledge about derivatives into these multivariable functions, into surfaces in R3 rather than curves in R2. And one of the ideas that we come across in Calc 1 is that everything looks differentiable. Everything that's differentiable looks linear if you zoom in enough. So if we switch over to a function that I forgot to put in. This is why I shouldn't have 8 o'clock classes. But then I realized this is also why I shouldn't have 9 o'clock classes or 10 o'clock classes or 11 o'clock classes and so on. So let's take a look at our graphing calculator. So here's our graphing calculator. And I want to look at the function y equals e to the x at the point where x is equal to 0. We know the tangent line is y equals, we have a slope of 1 and a y-intercept of 1. So that's the best linear approximation to the function e to the x near x equals 0. We have this curve, and near 0, that curve is very close to the line x plus 1. As we move away from 0, not so close. But if we zoom in close enough, we can't distinguish the line from the function e to the x. And the more we zoom in, the less we can tell the difference. This is why I don't do this on the TI-84, because the TI-84, the difference disappears really fast. So here we have more resolution. Look how close we are. And even with this high resolution, super high tech computer monitor, between negative 0.101 and 0.01, the graph and the function look the same. Even though e to the x is most definitely not a linear function, if we look close enough, it looks linear. If we zoom in close enough, things look linear. We just need to, even though zooming out, it's definitely not. We experience this on a large scale, and we're just trying to adapt to that. When we're standing on the surface of the Earth in a big field, less so in San Francisco, but more in say in Chicago, You're standing out in a field near Chicago, everything looks flat. It looks like you're standing on a plane. And we even just call it a plane, even though we spell it differently. It looks flat when you're standing out on a plane. But that's because we're zoomed in really far. And so when we look around, everything looks flat because we are very small compared to the round earth that we're standing on. Because we're looking at it from this perspective, or even closer. It's only when we get really far away that we can see we were not standing on a plane, we were standing on a curved surface. We were just looking so close, it looked flat. If you look close enough, everything that's differentiable looks linear. Now, if we look at a function, say y equals the absolute value of x, here's a function that's not differentiable. So if we zoom in at the point where it's not differentiable, it's never going to look linear because it's not differentiable. We can't just approximate it with one line. It's always going to look pointy. No matter how far we zoom in, this is always going to look pointy. So here we're zoomed in from -2 times 10 to the -6 to +2 times 10 to the -6, and we can still see that it is pointy. That's the refinement of differentiability over continuous. This function is not differentiable at the point 0. So even though we zoom in really far, it's a pretty impressive amount of zoom here. Even though we zoom in really far, it never looks like a nice flat line. There's no one tangent line that we could stick at this point. So the idea is everything that's differentiable looks linear if you zoom in close enough. So when we're finding the equation, just like before, we want to find the equation of a tangent, a line tangent to a one-dimensional curve in R2. Just like standing out in a field in the Midwest, we're going to approximate a surface with a plane in R3. So if you would recall, the equation of the line tangent to a curve given by this function, say y equals f of x, at the point x naught, f of x naught is y equals, start off at f of x naught, the slope is the derivative evaluated at the point, and we just write the point slope equation of the line. Start at x naught and go at, in this direction, f prime at x naught as you move away from x naught. We're going to update this one-dimensional line tangent to this one-dimensional curve in R2 with a two-dimensional plane tangent to a two-dimensional surface in R3. So if we want the equation of the plane, tangent to the surface, z is f at x naught, or x y at the points x naught, y naught, f of x naught, y naught. We're going to construct it in the same way. When we had one variable, we had a function of one variable, we just had one derivative to worry about. But now that we have a function of two variables, we have two derivatives to worry about. So we construct the linear function the same way. We take our starting point, f at x naught, y naught. And then we just look at the two different changes. We look at the derivative in the x direction at that point. So fx at x naught, y naught is how the function is changing in the x direction. And so that only has to do with x, the variable x, because we're only looking at how things are changing in the x direction. Only deals with the variable x. And then we also have fy at x naught, y naught times y minus y naught. So we construct the linear function or the linear approximation the same way we constructed the tangent line. We construct the tangent plane the same way as we construct the tangent line. So really, we're just adding more terms. Any questions? All right. Everybody's blurry. Now everybody's less blurry. All right. So I'm working on fixing the homework for unlimited attempts, and then I'll get the homework for 14.2 and 14.3 up. This weekend, you should work on those assignments, work on getting caught up on the previous assignments. I'm working on another quiz that should show up to work for you to work on this weekend. So lots to do in the calculus department. Any questions before we adjourn for the week, since today is Thursday? All right, well, that's going to do it for today. I'll see y'all on Monday. Everybody have a good weekend, and thanks for playing.